y into dx plus dg by dy. That will give you, but df by dy is equal to n. Substitute this and we will get n is equal to integral dm by dy dx plus dg dy. That integrating these equations we get gy is equal to integral of n minus integral delta m by delta y dx, again integration with y. Thus we obtain the gy. Substitute gy in the value of fy, we will get fy is equal to integral m dx plus integral n minus integral delta m by delta y dx dy. Thus fxy is equal to some arbitrary constant c is the general solution of given exact differential equation. Similarly, if we take df by dy and is equal to n and integrate we have to y and then substitute the values, we get fxy is equal to integral n dy plus integral m minus delta n by delta x dy whole dx integral. That is if we take another equations. So that
we take example.
This
Let us take example. Let us take examples.
Let us take examples.
So now we have seen the differential equation of the type m dx plus n dy equal to 0, right? So it becomes exact differential equation if the condition my equal to nx is satisfied, and the solution in that case how it is given. Now we see examples for that, for the exact, how to check exactness and then to give solution for an exact differential equation. But before that, for an exact differential equation we simplify the condition for solution. That is how we can easily write the solution from the coefficients m and n. So for an exact differential equation m dx plus n dy equal to 0, the solution is given by fxy equal to c, where f is function of x and y, and it is given by, from the equation m dx plus n dy equal to 0, we consider m and n, and using this m and n we can give the solution as fxy is equal to integral m dx. Here in the first term integral m dx, we integrate m, which is function of x and y, two variables. We integrate this m with respect to x, and at that time we treat y as constant. The second term is integral n minus integral my dx. This my means partial derivative of m with respect to y, and then dy. So we simplify the right hand side and the term n minus integral my dx there. So if you consider the term n minus integral my dx, that will be equal to n minus integral nx dx. As the equation is exact, we have the condition my equal to nx, so we have this. But n minus integral nx dx, that is nothing but the terms in n not containing x. For example, we see if we consider n as 2x plus y square equal to xy, then n minus integral partial derivative of n with respect to x dx, that will be 2x plus y square plus xy, that is value of n, minus integral of n x, that is partial derivative of 2x plus y square plus xy with respect to x. So partial derivative of first term 2x is 2, y square has its derivative with respect to x 0 partially, and xy's partial derivative is y. So at last we have y square, that is the term in n that is free from x. So now we consider this condition, this as the solution for exact differential equation. So the solution of an exact differential equation m dx plus n dy equal to 0 is given by, using this m and n, it is given by integral m dx plus integral of the terms in n not containing x with respect to y is equal to c, where c is the arbitrary constant. Here in the solution of a first order exact differential equation we get single arbitrary constant, because we recall the relation that the number of arbitrary constants in general solution of an ordinary differential equation that will be exactly equal to the order of the differential equation. Now we go for the examples. So first one, first is x square minus 2xy plus 3y square dx plus 4y cube plus 6xy minus x square dy equal to 0. So this equation is already in the form m dx plus n dy is equal to 0. So comparing the given equation with m dx plus n dy equal to 0, we have m equal to x square minus 2xy plus 3y square and n equal to 4y cube plus 6xy minus x square. So here we find the partial derivative of m with respect to y, that is my, and partial derivative of n with respect to x, that is nx. So expressions of my and nx, as we see, they are the same, and this implies that the given differential equation is exact differential equation, and so we can give the solution by the condition that we derived earlier. Therefore, the general solution of exact differential equation m dx plus n dy equal to 0 is given by integral m dx plus integral of the terms in n not containing x, its integration with respect to y, it is equal to the arbitrary constant c. So m is x square minus 2xy plus 3y square, so its integration with respect to x, and in this expression of m, wherever there is y, we will treat y as constant, plus integral 4y cube dy. See, you can see in n the only term free from x is 4y cube, so we have considered in the second term integral 4y cube dy is equal to c. So integration of x square with respect to x, x cube by 3, and integration of minus 2xy with respect to x treating y as constant is x square by 2, so it becomes minus x square by y, second term in the solution, plus integration of 3y square with respect to x, as we are treating y as constant, it is 3y square x, plus integration of 4y cube with respect to y, it is y raised to 4 by 4, so it becomes y raised to 4 is equal to c. So the general solution of the first exact differential equation is x cube by 3 minus x square y plus 3y square x plus y raised to 4 is equal to c. Now we consider one more example of exact differential equation. So the second example is it is again in m dx plus n dy equal to 0 form. You see, if the differential equation is not in the form m dx plus n dy equal to 0, you first set the form m dx plus n dy equal to 0 and then compare it with m dx plus n dy equal to 0 to get m and n, the coefficients of dx and dy from the first order differential equation, to check the exactness. So comparing the given equation with m dx plus n dy equal to 0, we have expression of m as sec x into tan x into tan y minus e raised to x, and expression for n is sec x into sec square y. So here, finding the first order partial derivatives of m and n with respect to y and x partially, we have the same expressions, and hence this equation is also an exact differential equation. So with the same formula, integral m dx plus integral of the terms in n not containing y with respect to y is equal to arbitrary constant will give us the solution. So integral m dx plus integral terms of n not containing x dy equal to c will give solution. So m has the expression sec x tan y. In this expression, tan y will be treated as constant, and integration of sec x tan x will be sec x because derivative of sec x is sec x tan x. So this is relation between integral and integration and differentiation. Minus e raised to x has its integration e raised to x. The last terms of n not containing x. If we recall the expression of n, it is sec x into sec square y. The single term is there in n and it is not free from x, and so there is no term. So we consider that its coefficient or that term as 0. The term of n not containing x, it is 0, and so its integration is 0, and so the solution becomes sec x tan y minus e raised to x is equal to c. Now here there are two examples for you to practice. First is 1 plus e raised to x by y, this is coefficient of dx, plus e raised to x by y into 1 minus x by y, this is coefficient of dy, is equal to 0. You will check exactness of this differential equation and you will also find its solution. And second is not in the form m dx plus n dy equal to 0. It is dy by dx plus y cos x plus sin y plus y upon sin x plus x cos y plus x is equal to 0. So for the second equation, first you have to write that equation in the form m dx plus n dy equal to 0, then get the expressions of m and n and check the condition my equal to nx or not. If it is there, then it is exact differential equation, and the solution is these both are exact differential equations. You will find them their solutions. So next topic is how to reduce the differential equations which are not exact to exact differential equations using integrating factors.
Let us suppose that while we check the condition of exactness, the equation, first order equation m dx plus n dy is not exact, then the solution does not exist in general. But sometimes it is possible that if we multiply throughout this equation by some factor, some function of x, y, then the equation become exact. Then by factor which we are multiplying to this to make the not exact equation to exact is called the integrating factor. Let f, the function of x, y, be integrating factor. Then the first order differential equation m dx plus n dy is equal to 0 becomes f into m dx plus f into n dy is equal to 0, and at this equation become exact, it should satisfy condition of the exactness. Therefore fm product, partial derivative of this product with respect to y, must be equal to fn product its partial derivative to x. If these two are equal, then it become a exact. Therefore simplify this, we get fy m plus m f my is equal to fx n plus f into nx, and simplify it, we will get m fy minus n fx is equal to f into bracket nx minus my. If the function fxy can be obtained from previous equation, the equation m f dx plus n f dy 0 become exact and its solution is possible. The equation m fy minus n fx is equal to f into bracket nx minus my is difficult to solve in general. Therefore let us take some simplification assumptions. Assume that f so function is function of x alone, then this condition or this equation becomes simplified, and after simplification we get df by dx is equal to my minus nx upon n into f. This part become function of x only, that is this part we will take as fx, and then df by dx is equal to f into p, that part is the px. Therefore, df by dx is equal to f into px, where px is equal to my minus nx upon n, and therefore, if you take integration of this, that will give df upon f into px. Integrating log of f is equal to integration of px dx. Therefore, f is equal to e raised to integral p dx. Therefore, this is the integrating factor. F is equal to e raised to integral p dx is known as integrating factor. If you multiply the original equation by this factor, it will become exact, and then by exact condition you can easily find the solution. Okay. I got it. If m dx plus n dy is 0 not exact, and m and n are homogeneous function of same degree, in this case also we can find out integrating factor, because dy by dx is equal to m upon n, or same homogeneous degree, we can write out this in this form, and ultimately it becomes the function of y upon x, and y upon x you can take v, that y is equal to vx you substitute, and then this equation become in terms of v and x instead of y and x, and it will become v plus x dv by dx is equal to minus m upon n, but m and n both are function of v now, and they are integrable. That will give you ultimately x dv by dx is equal to minus v d m upon v is equal to minus y upon x m upon n, and simplifies to xm plus yn upon xn, and this will dx upon x is equal to xn upon xm plus yn dv, and integrating this dx upon x dv upon m plus n, we get the integrating factor x into m plus y into n, it should not be equal to 0. Then 1 upon xm plus ny will become a integrating factor. This is only possible if the m and n both are homogeneous of same degree. Now, rules of integrating factor m dx plus n dy, will take note of all three rules here, and while over